All right. Good morning. My name is Eric Peter Wayagala, and we are here to talk about a topic in natural language processing, which is leveraging machine translation for medical translations. We had a couple of introductions about this particular topic in our first video. And this is a continuation of the video that we made earlier on. Now, with medical translations, it's a little bit hard to translate some of these terms to people who are in very rural communities, and machine translation systems seem not to capture well the translations of these terms that to make them a little bit understandable to the people. So this issue is very diverse in several domains. For example, in agriculture, in the medical health. But for this particular case study, we are going to look at the medical health, whereby the doctor during the prescription of drugs, sometimes they say a patient is supposed to take one tablet 3 times. And now, when this information is being translated to another language, sometimes there is a mistranslation, and the patients understand this information in a different way. So we intend to leverage machine translation systems from the dataset point of view, and also train models that are able to provide very good quality translations for this case. Now, there is no surprise with the sensitive nature of the contents in the medical domain. Translations are a little bit tricky, given the fact that very few people get to understand what some of these medical terms mean. Now, in many cases in this industry, where people are using machine translation systems like Google Translate, IBM, Facebook Translate, Meta Translate, these systems tend not to capture the context in which particular communities would understand these medical terms. Now, we managed to, for this case study, we are going to use an already existing data set, given the fact that we don't have an already curated data set for Ugandan languages. So we are going to use the UFL medical corpus, which is a collection of parallel corpora assembled during the course of the projects K-Connect, Cresmoy, and HML dataset. So basically, this dataset is parallel corpus from English to several languages like Hungarian, Spanish, German, Polish, Romanian, and Swedish. So each language is paired with English, of course, to form a parallel corpus for training a machine translation model. The data sets, though, consist of in-domain and out-domain parallel corpora. So with the in-domain parallel corpora, it comprises of the medical corpora. Of course, this is now the domain that we actually talking about. Then we have the out-domain, which is the general domain data set. So with this, we have data from text data from several domains like sports, policies, and so on and so forth. But in domain, this is particularly text concerning the medical terms and biomedical information and all that stuff. Now, some of the sources of these data sets, so the data sets were acquired through web crawling from the medical sites, and also open subtitles, for example, subtitles for movies, in case it is a movie about medicine or something like that. Now, with the data set is in thousands of rows of text data. But for this case study, we are going to choose one parallel corpus for example, English to Spanish or English to French, to be able to experiment on it. And we intend to use this the guidelines of the data curation used here to build our own data set for one of the most prominent Ugandan languages, which is Uganda. Now, the factors of selecting this data set, we considered the data set diversity, given the fact that the data set has the general concept in all the domains, and also the domain that we have. We talk about the domain of medicine. Now, the diversity is unlimited because the data set has thousands of data scraped from several sources of websites. Then it has a feature representation. Of course, this the representation of the medical terms or the medical texts that we actually intend to look out for in this particular case study. Then the dataset size. So the dataset size is actually enough to train a good neural machine translation model. Then the quality of the data set. So of course we have the parallel corpus, the English to German. Or for example, of course, the data set has sentences with which are well cleaned and already published. Then the reliability, of course, the data set does what exactly it's meant to do, to build a machine translation language with a source and a target language for this case. Now, some of the important features, of course, the dataset provides the domain adaptability. So we have the general outbound out domain sense, so such that we can capture data from several domains, and then these models can understand something from other domains. Then the translation of medical terms, of course, we have these translations that we are looking out, for example, translations about prescription, translation about biomedical information and all that. Then we have, of course, we have the parallel corpus. Yes, without this, we can't train the model. So it's an important feature that we have the source and the target language for this case. Now, my colleague Cosmas is going to take us through the Bayesian theorem and the rest of the part of the presentation. Thank you so much. Cosmas.
Yeah, thank you, Eric. So, as Eric explained, we are going to be dealing with machine translation in the medical field. So I'm going to tailor my discussion of the Bayesian theorem to the medical field. So the Bayesian theorem, like it's a rule for combining prior experience or information with current evidence, more of like information you already know, the past experience you know about something, to calculate the probability of a certain event occurring. So the condition probability that we know one thing about an event can be derived from knowing the other thing about the event. And here I'm going to go straight to a real life example as of now. Assume that probability PA, more probability of A, is the probability that Arsenal will win their next game. Probability of B is the probability that they won their last game. More of like currently we know the results of Arsenal's last game. So if we are to use the Bayesian theorem to find out the probability of Arsenal winning their next game, given that we already know the result in their previous game, which is noted as probability of Arsenal winning their next game, given that we know that they will win their next game, as you see P of A given that you have information about B, can equate to probability of A, given B equal to probability of A times probability of B given A, divide that by probability of B. More of like the numerator is divided by what you know. Yeah. So what you know, what you don't know out of what you know. More of like you have to use information about your past experience to calculate the conditional probability of something you want to know. So that's the Bayesian theorem. Speaking about its application, next slide. Its applications in the machine translation field, Bayesian theorem can be used in text classification in machine translation, especially in identifying words or sentences that are grammatically correct or vice versa. So you can use Bayesian theorem, given that you already know information about a correct grammatical sentence. You can use that information to know if this sentence, the sentence you want to predict, is grammatically correct or wrong. You always have to base on some prior information. So we go to naive Bayes. Naive Bayes, just a simple learning algorithm that uses Bayes rule with a strong assumption that the features are independent, which we call class conditional independence. So you have to assume that the input features are what? Are independent. That's why it's usually considered to be naive, because it ignores the relationships between these features, hence naive. So usually Bayesian theorem tends to have high bias. As you know, in machine language, bias usually resonates with the assumptions you make. So the more assumptions you make, the higher the bias, and low variance. And the low variance means that naive Bayes tends to be consistent with new data sets, new training data sets. Yeah. So it doesn't deviate so much when you introduce a new data set. It has a low variance. It's always consistent with new data, but it tends to have high bias due to the assumption, the class conditional independence assumption we've made. So in our aspect of machine translation in the medical field, we can use naive Bayes to predict text tags during machine translation by calculating the probability of each tag for each text and output the highest one. In this case, remember we are using clinical terms. The perfect example, we might have translated the word. Let me give you a scenario of the machine outputs two texts. One is mix well before you drink, and the other one is shake well before you drink. I think this is for syrup. In medical terms, those two sentences are different, but they are grammatically correct, but they are different. We can score one as being clinically correct and the other being clinically misleading. So you can use naive Bayes to do this, to predict these tags, so that the one which is more clinically correct, or in this case, can be the one which is output by the model. Next slide, Peter. So next is Bayesian networks. Bayesian networks, I think right from the word network, you know, a network has an aspect of a graph in it. So a Bayesian network is a graphical model for probabilistic relationships among a set of variables. Unlike naive Bayes, the Bayesian network models the relationships between input variables, where you have the nodes as the features and the edges are the dependencies between the nodes. So the nodes in the Bayesian network represent the variables of interest. In these variables might be something like grammar. In this case of ours, they can be pronouns, they can be rules, the grammatical rules, all these, and these can be modeled by a Bayesian network. Yeah, Bayesian networks perform well on incomplete data sets with strongly anti-correlated variables. So they happen to, as you provide more data, they happen to establish these relationships between the inputs. Yeah, next slide, Eric. So we are going to look at the difference between Bayesian theorem and naive Bayes. Naive Bayes assumes conditional independence of classes, while Bayesian theorem does not. Bayesian theorem doesn't make an assumption of conditional independence of features. In Bayes theorem, we calculate a single conditional probability given all features, while in naive Bayes, it's simplified by calculating the conditional probability of each, and then we multiply them together as we expressed in this image below. As you can see in Bayes theorem, we don't assume that these features are independent. Yeah. And in naive Bayes, we simplify that by assuming that independence, which is sometimes meant to increase computational output. That's why naive Bayes is fast. It's fast due to that assumption of conditional independence of classes. Next slide, Eric. Now the difference between naive, I'm going to discuss the difference between naive Bayes and the Bayesian networks. As you can notice, the Bayesian networks model independence between input features. And yet, naive Bayes assumes independence, and yet the Bayesian network more of models the dependence between these features. So we conclude by saying that naive Bayes is more of a constrained version of the Bayesian network, where the class nodes have no parents and the nodes corresponding to attribute values have no edges between them. Since we have assumed they are independent, yeah, the difference comes in the way we model these. So just naive Bayes, just the conclusion is that naive Bayes is just a constrained version of the Bayesian network, where the nodes have no parents and the nodes corresponding to attribute values have no edges between them. Yeah. Next slide, Eric. Application of the Bayesian network specifically to our research topic, which is leveraging machine translation in the medical aspect. So we see that we shall need Bayesian networks to model the language rules and constraints like pronouns, the language rules, like where to place a full stop. You can only model such relationships by identifying the dependencies between them, and this is where the Bayesian networks come in. So we shall apply Bayesian networks when it comes to modeling language rules and constraints. Yeah. Next slide, Eric. Here we just list a couple of journals and papers we cited and where we got the information from, and where we read to more of understand these concepts. Yeah, I think that's all we had for you for this presentation.
Thank you so much, Cosmas. So one of the most straightforward application of Bayesian theorem and naive Bayes is in the statistical machine translation. So there we use probabilities to actually get, we use the component of probability to get the translations out of the models. Thank you so much. We hope to see you soon in our next video.